All right, so questions. Hello, welcome. Happy Monday. Questions. No questions, good.
Something's not quite a question, more something I noticed. A bunch of us ran our Pt2 on War and Peace, and we noticed that at the end of the output was always chapter with one occurrence. So like if we looked at it with octal dump, it was like
Oh, it had stuff in the beginning? Yeah, interesting. Cool. You can strip that stuff out before you process. But yeah, the way that we wrote the assignment, all that stuff is fair game, so whatever it decides to call a token is acceptable. But that's kind of cool. Well, okay, so what are we doing this week? I want to talk about PA2, give you a rundown on that, go through some sample code. I want to take a look at Lab 3, and then I want to talk about threads today, and that's going to be our main topic, is threads and threaded programming. And that'll take us into other areas. And then Wednesday, we'll probably continue talking about threads. I want to talk about statics and get those out of the way. And then we'll move to looking at some built-in classes for handling things like lists and hashes and things like that. And then we're going to go back and we're going to revisit trees and data structures. And by then it'll be a few weeks from now, so I don't know what's going to happen after that. But I want to start off with PA2 and talking about that assignment and showing you some code. So general synopsis of PA2, right? Really good work. Worked well in most cases. And as you might expect with PA2, it kind of works or it doesn't work. There are odd cases where it sort of starts to work and then something breaks. But in general, if it doesn't work, chances are it doesn't even compile, right? Or it gives you a null pointer exception as soon as you run. If it's taking in input, there's a good chance that it's, 70, 80, 90% correct, if not 100. So let me show you a version of this that I put together. And let me show you some test code. So to run this, so first of all, if you're getting a message that you can't see, if you get a message like this, anybody gotten this before where you try to run something that says can't be launched?
Yes.
Yeah. So
Isn't it that you're on the main or something?
heck, I'm keeping the lights off, man. It's that kind of day. So sometimes if you click on your main class and try to run, that will work. If not, you can right click on your class and say run as and say Java application, and that generally seems to work. And then I'm going to click in here and I'm going to paste in my text, except I'm not. So I'll grab that here. All right, if Control-D, Control-Z is not working, right, when you're ready to end your input, okay, you got to be at the beginning of a line. You can't hit Control-D at the end of a line. We learned this in 224, right? The end of file indication is always when you're at the beginning of an input line. So hit Enter after your last line of text, and then just click in your code, click back down here, hit your end of line character. And that, everybody that I've worked with, that seems to work now, okay? So in this case, it does the indexing on this stream of words. So that's just a sample test file. Important that you test with more than 2 occurrences of your word. because a linked list with two things is edge cases, right? An empty linked list, a list with only one node, or a list with only one node and an end node, those are all kind of edge cases. It's really when you get to a list with three things in it that you start having to deal with some subtleties that can trip you up in your code. So there are some cases where it only picked up 2 occurrences of each word, right? But in your position list you should be testing independently of the whole PA2 assignment. You make a position list class, and now you just shove integers into it, and you keep calling your print method or whatever you're doing to output it, and make sure it's doing exactly what a linked list of integers should work. And if that's working, right, then you're just using it in your word list code. All right, one more comment since we're in here. If your Control-Z, Control-D is absolutely not working, right, and for some reason on mine sometimes it breaks when I was running people's code. So window preferences, come up here, find keys, come over here and search for EOF. And in some cases this was missing, so EOF sends end a file, I've got it bound to Control-D when I'm in the console view. In some cases I'd import someone's project and it wouldn't recognize Control-D, and I'd look and this was blank. Right, so find that and come down here to the binding, hit Control-D, select in console view and apply, and that seems to restore it. Or if you hate Control-D, you could make it something else. All right, so let's eyeball this code. So the main method is straight out of the assignment, right? Build an index utility, construct an index utility, and then use the build index method from there to get a word list, and then use the print method in the word list. So it's literally 3 lines of code for the main program. So index utility is the workhorse top layer. And it has one object inside, which is a word list, and I called it the list. The list should never be null, okay? There's always a word list. Setting something equal to null is different from saying that you have an empty word list, okay? It's like having an empty car versus no car. Okay, so I always want a word list. It's called the list. I'm going to construct it in the constructor for build index right here. So the list is not null. It's an actual word list, but it may represent an empty word list. If there's no words in the input, then the linked list that's inside word list will, have a first node that's null. Okay, but the list is the name of the list. This is a temporary. This is my scanner object for system.in. This is a running count of where each word occurs. And then this is the main loop. So I called hasNext to see if there's another token. So a token is stuff separated by the default delimiter, which is white space. So if there is another token, I say s.next to get that token. I convert it to lowercase. I went ahead and saved it in this string called word. And then I called the add method on my word list, so the list.add, and added that word at the next word number position. And that loop repeats until hasNext comes back with false, and then I close the scanner and then return the word list. So that's the whole indexing top level behavior. Some people chose to do hasNext line and next line and pulled in their input one line at a time and then broke it up manually. You can do that, but there's a few downsides. One, when we're tokenizing with hasNext, it's breaking at white space, so tabs, vertical, form feeds, new lines, and things like that. If you just use a split with a space, that's not going to give you the same behavior. I didn't take off for that. The other disadvantage is when you use split on a string, it builds an array. And if I have War and Peace on a single line that comes back from hasNext line and next line, and then you split that into an array, it's going to be a big array. You could get into memory issues. Okay, that makes sense if for some reason you need to be saving these words and going back to them later on. But the basic processing of this build index is get a word, add it to my list. Get a word, add it to my list. And you never really need to go back to one of these words you've already gotten. So why save it in memory? You can deal with it and then just go on to the next word. So simpler, sometimes better. Simpler, but not too simple, right? So then word list, this is where all the good stuff happens, right? So it has a single variable header, which is a word list node. So I suggested splitting your classes into pairs. Have a word list and have a word list node. Have a position list and have a position list node. And not everybody did that, and you can get away without doing that. You can treat your position list as a position list node. But it's really kind of working despite not really being what you want, right? But I mean, a word list has this node in it, right, which we call a header, which means we can store words in there and stuff like that. But it's cleaner to have a list in a node, right? And especially when we get to trees. So so my header is a word list node. It's initialized to null, so I didn't use a sentinel. If you use a sentinel, then you'd initialize this to an actual word list node that you just don't use. And then there's one big method. Print's not a big deal, but the main method is add. So add will add a word at this position to our list of lists. And what that means depends on whether or not the word exists in the list already. If it doesn't exist, we create a new node in the right spot and we set its position to num. If that word does exist in the list, then we just add num to the end of the position list. So if the header is null, meaning that our list is completely empty right now, then we want to make a new word list node, and that becomes the entire list. So the constructor for a word list node will take a word and a position, and it will build a node that, well, it'll do all of this. This is the constructor for a word list node. So it creates a word list node with the word stored here, a null stored in the next field, and this thing pointing to a position list with a number and a null. So the constructor gives you all of that stuff, which means we're ready to start tacking position list nodes onto there, and so on. So if we're starting with a completely empty list, where the header is null, then this new word list node is the whole list of lists, right? So we just set that to the header and we return. Otherwise, we're going to have to march through and look for our words, so I used a pair of nodes, previous and current. And since I don't have a sentinel, my first node I need to check is the one that's actually the first node of the list. So there is no previous node to that, right? So when you first begin this, here's ant, and here's cat, and here's dog. And if I'm inserting the word bat, right, I'm going to come down eventually and discover it should go before cat, and I'll have ant point to bat and bat points to cat. But if I was inserting something like AA, it's going to go before the very first node in my list, and there is no previous node that I'm going to change to point to this, right? It's an edge case. So in my code, I initialize my previous to be null, and that's a flag. When I find the node that I'm trying to insert before, I'm going to check previous, and if it's null, I know I'm inserting in the beginning of the list, and I'll do something different there. All right, so we've got a previous and current, and well, current is not null. So if this is not the right place to insert the word, and if the word is not equal to this node, right, then we're just going to march down the list. So move previous to be what your current node is, and move current to whatever the next node is, and we'll go back and we'll check again. Okay, so this has us moving down the list. each time we compare the word we're inserting to the word that's stored in that node. And if this compare to is bigger than 0, right, so let's go back to inserting that. So we're comparing the word in the list, okay, current.word, with the word we're trying to insert. So we're comparing, for example, cat to bat, or ant to bat, right? We're comparing the node's word to the word we're inserting. And compare to, right, it subtracts ASCII codes. So it's going to do this minus this. That's going to give you something positive. If our word was ant and we do ant minus bat, that's going to be 1 minus 2. That's going to be something negative. So when this subtraction gives us something bigger than 0, that tells us we should insert right before whatever current is. So that's this case right here, insert before current. So we make our new node, right? Make a word list with the word and the number. And we have its next field point to current because it's going before current. And then if the previous node is null, we know that this is the first node in the list now, so we just set the header point to it and we return. Otherwise, set the previous to point to our new node. So that's the standard pushing something in between two nodes in the linked list. And in either case, we return. Otherwise, we're not ready to insert before that node, but it's possible that our word equals this node. So if the current word is equal to the word we're inserting, now we just want to add a new reference. So we take the current node's position list, that's ref header, and we call the add method, and we just say add that number to the end of the list. And then we return, otherwise move down the list. And if we get all the way down here, we got to a point where current was equal to null, which means we didn't find our word in the list. It should go after the last node in the list, which is previous. So now we just set previous next to be this new word list node, and we're done. And you notice I didn't construct this new node in the beginning of all of this because we don't know if we need a new node. If we find the word, we're not going to use a new node, a new word list node. We're just going to update the position list. You could create it up here and it'll get garbage collected, but I chose to create it where we need it. Yeah?
Is it, so in a language that has a garbage collector like this, is it still better, like I know it's probably a better habit to get into, properly managing your data,
Yeah.
but like, you think like an employer would freak out if you relied on the garbage
Yeah,
collector?
definitely. For one thing, depending on how often you call this, if you were doing 1 million insertions a second, right, and most of the time you were just bumping up counts on words, but you were creating an extra garbage node every time, right, you could potentially impact the performance. But it would also, it would probably raise an eyebrow, maybe not freak out, but.
I've heard people saying you can call the garbage collector early, but Gavin is well enough to do it.
Yeah, and even if you could, it's still kind of a lot of overhead.
Yeah, I noticed there were a couple examples of people who called it early, and you still end up getting you run to the memory early, but there's fewer errors. But
Yeah.
you know, either way, the best practice is not to just.
Yeah, and it's easy to do if you think about it, right? You just not create the nodes until you need them. All right, so that's the add method. The print method is pretty straightforward. So this is the usual list traversal, right? Traversing a word list. So start off with temp at the header, and if it's not null, print out the word, a colon, and then the position list. So I'm punting to the toString method that I have in the position list, which will give me a comma-separated list of positions. Move down to the next node and repeat, and just do that until you run out of nodes. Yeah?
So you, at the end, you concatenate a print function. Is that a print function for your?
There's a toString method in position list.
Okay, because I had a print function for mine. Could I have put that in the?
Yeah, you could have called the print method.
Yeah, because I
of
called
the
it
position
outside
list.
of the system line. Because
Yeah.
that has its own system line
Mhm.
thing. Would that, if I had put it in this one, would it have messed with anything?
Well, you can't concatenate a print method here unless it's returning something.
Oh, okay.
But you could print out without the new line the word and the colon, and then you could call temp.refheader.print,
Okay.
and
So
that
that's-
would print out the list of numbers. And that's fine.
So that's the advantage of the two string. Is you can
Yeah, it's kind of in place.
Okay.
Plus, it's part of like a general linked list of integers class,
Okay.
right? So if you want to do something else with it, like if you were debugging or something, it might be useful. All right, so the word list node, not a lot going on. We've got a word, we've got a next field, which is a word list node, and we've got a ref header, which is a position list. The constructor, as we said, takes a word and a position and sets the word to the word field, sets the next field to null just for good practice, constructs a new position list and sets the ref header to that, and then immediately calls the add method to add that position to the first node. So that's why when you construct a word list node, you get this whole structure for you with the word, the null, and then a pointer to a reference list that has that number stored in the first position list node. So that does all of that for you. And then position list, good old linked list of integers. So it has a header, again, no sentinel. Constructor set the header to null. And then the add method, here we know that we're going to make a new node, so I created that node up top, create a new position list node with that number. If the header's null, just set the header to that new node and return, right? It's the first node. That's never going to happen in this case, right? Because, well, no, it will happen. I changed it because we add to an empty list. Okay, that's fine. And if the header's not null, then you have to follow through until you get to the end. So I set the temp to the header, and I check to see, well, temp next is not null. So I know temp's not null, so this is a safe thing to do. But I'm going to move through until I get to a node, temp, which says the next field is null. At that point, temp is the last node. Okay? And since temp's the last node, I can just say temp next equals whatever our new node is. Right? Otherwise, move temp down the list and keep going. So that sticks your new node on the end of the list. And then the toString method, if the header's completely null, there's nothing in the position list, just return a blank line. And that won't happen in this case because our position list always has at least one node, otherwise it doesn't exist. But in general, that'll do the right thing. And then again, set temporary to the header. Set the output to the data stored in that first node, and then move to the second node, and as long as it's not null, I go ahead and concatenate a comma and that node's data to the output, and then move to the next node. So first thing we do is take the first node's data, stick that in an output string, and then we loop through all the remaining nodes, and for each node we concatenate a comma followed by that node's data. Okay, so this is giving us a comma-separated list. We're putting the comma on before the data, so we don't have a trailing comma problem. And when you get to a point where the node's null, then we just return that output string. And then position list node, just save the number in the data field, set the next field to null, and you're done. All right, so integer list. All right, so that's a version. If your PA2 was not working completely, right, definitely come and talk to me this week, okay, early as possible, and let's work through your code. I said most of the time if your code doesn't throw up right in the very beginning, it probably works mostly right. But you can have one extra line or one missing line that completely changes the behavior of your code. And sometimes it can be subtle, like you only see 2 entries for each word, even though the word appears more than 2 times. And so I was helping someone this morning with that, and it was one extra line of code they had that was left over from a debug, or from an earlier version, right? So it can be really, really subtle. But the way you debug is not by trying to change lines of code until it works, right? So it's going through your code step by step and seeing what's making sense, or it's going to the debugger and stepping through, right? So my third reference to this thing isn't showing up, so you step through to the point where you get the third reference, and you go line by line, you watch how your structures change. And when you see a change that you didn't expect, then you back up and say, okay, what's the code doing? Do you know about the rubber duck method of debugging?
Yeah.
Okay,
Explain
so,
the code to rubber duck.
yeah, so you get a rubber duck. I used to use a teddy bear, right? And you put it down in front of you and you just describe your code to it. You talk through your code, but the process of verbalizing it, right, to somebody else can help you get out of the habit of, here's what the code is, but what I see is what I think the code is doing, right? So I'll say, and here we move down to the next node of the list, even though the code doesn't say that, right? So if you're going line by line and explaining it to someone or to a teddy bear, you may more easily notice that, like, you don't actually go to the next node of the list. You just go back up and check to see if it's null again. And it's like, oh, I guess I never moved down the list.
Or a picture of Teddy Roosevelt.
A what?
Or you can talk to a picture of Teddy Roosevelt.
Picture of Teddy Roosevelt might work.
The OG Teddy Bear.
But then if you hug it when you get your bug solved, it looks a little weird. All right, so questions on any of that?
So, I guess like, what's my question? So two-string,
Yeah.
when you call that in your print line,
Mm-hmm.
it's automatically called as the nature of being two-string. When you concatenate your data, it's automatically gonna run whatever while loop you have sitting in your two-string
Yeah.
as a position list.
Mm-hmm.
That's a much better method than doing print.
Yeah, it's kind of
Later.
cool, right?
Yeah.
Because you get this code invoked for free, and yeah. So we could have done that with the word list too. And then instead of having a print method, I could have just said, have a two-string method.
Could have done it a few lines of code.
Yeah. All right, so I want to talk about threads this week. And part of the reason for talking about threads is for lab 3. So let's look at lab 3 first. So lab 3 is very much like lab 2, the blinking LED, with one modification. So at the end of lab 2, you prompted the user for a blink rate, they type it in, and then you blink the LED according to that rate, right? In lab 3, while the LED is blinking, the user can change their mind, type in a new blink rate, and it'll adjust the blink rate automatically. So the LED is blinking, you type 50, hit enter, it starts blinking really fast. You type 1,000, hit enter, it starts blinking on a second, off a second, and so on. And you can do this indefinitely. So the setup is the same, the sign off is there. The wiring, right, pins 14 and 16, all that's the same. The code's gonna definitely be different. So here's some C code that we use for reading input. And let's do something like, let's do a print before. And we'll do a print after. Okay, here's the thing with doing input in most languages. When you get to this line of code where it says fgets, your program is not going to make any more progress until the user hits the enter key. Okay, there's a line right here waiting to do something to print out by, but that code does not execute because you're stuck inside this call to fgets. Alright, so this is called a blocking read. It's blocking in the sense that it's blocking your program from proceeding on to the next line of code. And if you do a get car, right, it'll block for one character. If you do an fgets, it'll block for more potentially. But the essential point is that your program is stuck inside this call to fgets. Okay, if you were to look at your machine language, your program counter would be somewhere inside that function, right? And it's waiting to return from fgets before it can continue with your program. Most input that we do in high-level languages is blocking by nature. And it makes sense, right? If you have a program that's supposed to add two numbers together and it says enter the first number, you don't really want your program to go on through the rest of your code until the person's entered the first number, right? I mean, it wouldn't make any sense. So by design, when you do input, you usually sit inside that call to the input until the user satisfies the input requirement, hitting enter typically. For an LED lab like Lab 3, that's a problem. Because here's the first version of Lab 3. So read a blank rate. Let's store that in a variable n. LED on. Sleep for n. LED off. Sleep for n. And well, if we go back up here, our LED is blinking now, but if we don't do another read, the user can't change the blink rate. And if we come all the way back up here, the LED turns on, waits, turns off, waits, and now the LED is not blinking because we're sitting inside this read call, this get next or this fgetC or something that's waiting for the user to type in a new number. So with this kind of conventional approach to programming, we can't really do Lab 3 unless we have a non-blocking read. Which would mean instead of saying something like fgets, we'd say, is there a number available? And if there is, we'd say fgets. If there's not, then we'll just go on and blink the LED. We don't want to deal with non-blocking reads. They're messy, they're error prone, and mostly they're just complicated. And they're not cool like threads. So we're going to take a different approach to this, which is to use threads. And the idea is we're going to have a process that's doing this. But we're going to have a second process which says read the blink rate. Save that in some variable n. And it's just going to sit there and it's just going to get blink rates from the user. But somehow, once the user types in a number and hits enter, that new number is going to get sent to this thread. And it's going to somehow change the value that this thing sleeps, the amount of time it sleeps. Alright, so how do we do threads in Java? Really easy. Use the thread class. So let's write some code. So we'll make a main method. Alright, so my main method is going to create a new object of type myThread. It's going to run a go method in myThread, and then it's going to say goodbye. So let's create this myThread class. So what's our go method going to do? It's going to print out 100 integers. How about that? So it'll loop from 0 to 99. It'll print out the integers side by side, and it'll print out a new line at the end. All right. Not a big surprise what happens here. We run this. It calls the go method. The go method prints out 100 numbers. There's 57 more numbers over there, 56. And then it says main is exiting goodbye. No surprises, right? Now my thread, I'm going to say extends thread. Which means, remember when you extend a class, you get all the stuff that's in that class. So my thread is much more than just this one method now. It's a bunch of other methods. So if I do mt dot and I hit my control space, I see all the methods that are available to run in this myThread object. So one of them is go. That's the one that I created. But there's all these other methods also, including something called run. So if I say mt.run, nothing's going to happen. Right? The default run method of a thread is boring. So if instead of having a method called go, I have a method called run, this is still doing what we had in the first case. And that shouldn't be surprising either. I have a method named run, and over here I'm saying let's go ahead and execute the run method. And it runs and it prints out 100 numbers, and then that's done and my main program exits. Yes?
You just turn it into extend.
So when you extend another class, you inherit all the stuff that's in that class. So if I don't say this, and I look at my MT object, right? It's got a few methods available to it. It's got mostly methods that it inherited because it's an object, and it's got this run method that it inherited from my thread. Okay, but that's it. But as soon as I say that it extends thread, suddenly I've got a whole slew of other objects that it's inherited from thread, like get stack trace and get thread group and all this other stuff. So I have a much richer class than what I've written right now, because it has all these things in threads. So at this point, I've got a method named run that does this printout, and from my main program, I run that run method, and it does exactly what you'd expect, right? Okay, I'm going to make one change here. This is subtle. Instead of calling run, I'm going to call start. And I haven't written a start method over here. My only method I've defined is run. But watch what happens when I run the start method. So two things happened here. One, it still executed my run method. But two, my main method executed right away, even before that run method actually started. So what happened here was we created a second thread. So when you have the thread class or something that extends the thread class, there's a method available called start. You don't write start yourself, you just inherit that from the thread class. But when you run the start method, two things happen. One, it creates a new thread. And two, it executes the run method.
Has to be called run.
Has to be called run, has to be public void run. and then it executes that run method in that thread.
Can you go back there a little bit?
Executes the run method in that thread.
Is there like a run 1, run 2, run 3, so you can run as many threads as you want?
Don't need to. So run creates a thread. Start creates a thread for the MT objects run method to run. But I could do the following. Right, I can make 3 MT objects. And then I can start all 3 of those. Well, if I run that, I'm going to get a weird mishmash of output.
It's like they're racing.
They're racing. So I got up to 33 here, and then I went back to 0 and did some output from there and got up to 88. And then my main program exited, and then I went back to 0, and then I continued with 89 somewhere down here. And things are happening in their own kind of order. And if I run this again, I get something very different looking, right? It looks like 3 things happen sequentially this time, with main exiting between the first and the second. And if I run it again, I get something even stranger. Main exited right away. So let's add some diagnostics to this. Instead of just creating 3 threads, I'm going to name these threads. So we'll call this one Bob, and we'll call this one Mary, and we'll call this one, I don't know, what should we call this one? Sue. All right, so we've got 3 threads now with names. And how am I going to save those names? Constructor. So we'll have a name for each thread. And when we construct, we pass that name, and we're going to save it in our variable named name. And down here, when we do our printout, we'll print out the name along with the value of I. And so now you can get a little better idea of what's going on. Right? Mary gets first shot at this, and we constructed Bob, Mary, Sue. I don't know what happened to Bob, but Mary got first shot at this and ran all the way to instance 94, and then all of a sudden Bob came in and said, "Hey, I'm here too," and then Sue came in.
There's a word wrap in the console.
There's a what?
There's a word wrap.
Oh yeah, there is. And I think I have my tooltips back. Yeah, I do. Word wrap. There we go.
Oh, there we go.
So this is all over the place, right? Bob got a really late start and then ended up finishing right here. And then Sue came in and finished, and then Mary finished, even though Mary started. And again, if we run this again, we get something totally different. Okay, so here's an important lesson, right? When you're trying to debug threaded code, you have to understand that probably your code is not going to do the same thing 2 times in a row. In fact, it'll probably never do exactly the same thing. Which means if it fails once in a while, you've got an extra challenge to debugging, which is trying to isolate some sort of condition that you can debug around. Okay, or putting something in your code to detect when it's failing so that you can put a breakpoint there and try to get some handle on it, but it's notoriously challenging.
It's kind of hard to understand where like a computer program does what you tell it to do and
Mhm.
doesn't do things that it wants to do.
Mm-hmm.
And so how is the output different every single time when you're doing the same thing?
So here's what's happening when you have these threads. You're actually creating separate independent processes.
Like, wouldn't it start in the same order?
Well,
I mean, clearly it doesn't, but I don't.
so think about C, right? We have a fork statement in C. And fork clones a process and then we do something to change its behavior, right? But when you say fork in a C program, you create a new process, right? Process ID 17 was the original, now you got a process ID 20, right? And you have two processes now sitting in your operating system. What is it that controls when each process is executing? It's partially up to the operating system. So the operating system will give this process a certain amount of time, and then an alarm goes off and it says, okay, your time's up, throws it off into memory, says, who's next? Oh yeah, process 20, and process 20 runs for a little bit. But the timing of that, exactly how far will each process get, is usually based on time. So how many steps will they get depends on what else is going on in the system. If I start getting an email at the beginning of this process's quanta of time, it may make a tiny little bit of progress. The email client kicks in and starts getting priority, and when it finishes, this thing's quanta of time is done, and right? So it can be all over the place.
So they're acting kind of like low-level interrupts to each other.
Yeah,
They
yeah.
have so many cycles to do what they want before
Mhm.
something else comes along.
Right.
Okay.
And if I move the mouse while this is running, or if the clock ticks over and it has to bump up a number of seconds or things like that, right? There's lots of potential variables here. So it's not random per se, it's deterministic, but to us it's effectively random, right? Same as a coin toss. It's not randomly coming down heads or tails, but we can't quickly calculate all the forces and physics and figure out where it's going to be, so it looks random. Now on a old style CPU with just a single core, right, you don't really have parallel execution. There's only one thing happening at a time. Could be the operating system, could be your main thread, could be your parallel thread, right? On a multi-core system, they're actually running simultaneously, probably, right? If your JVM is good and knows that you have 4 cores, you might be able to run 3 or 4 threads simultaneously, and they're actually executing in parallel, not back and forth. And then it's even more unpredictable as to what the order is going to be.
That makes sense when the Pentium 4 came out, Intel was
Yeah.
typing up the hyper-threading and all that
Yeah,
stuff.
yeah.
That makes sense.
So what would happen if you threaded like 60 threads with that rate?
No, you can do that.
Ah.
Threads in a for loop?
What have you
Let's
Give
see.
them all random names too while we're at it.
Oh, I like that. Can you generate random names?
These guys.
I can't call it new.
You should do
We'll just call it the square of I. How about that? Here we go. So we got 60 threads going plus Bob, Mary, and Sue.
Is it gonna mess up that you're declaring a new MP?
No, it's an object.
Once it starts, you don't need it.
Once it starts, you don't really need it unless I want to do something with that thread from here. So the old object will get garbage collected when it exits. But we can run that, and it didn't seem like a big deal to it.
Take too long at all.
Yeah.
What if
So
we set that to 2000?
that's taking it a little longer.
My CPU would get
Oh,
Yeah.
uh-oh, yours didn't like that.
No.
Did yours die?
Yes, it did.
Do you want to exit the workbench?
No.
literally kill my
Cool.
computer, run my battery down.
So let's see what this did to our process space.
Everything just imploded.
Yeah, not too bad.
Cover your eyes. Computer connection screws
All right, so let's take a 5-minute break, and then we'll talk about some details on this stuff.
Uh-oh, okay.
Are we talking about any more stuff